Alright, so we're going to be first talking about refractive index and Snell's law, which is basically going to be your introduction to your reflection and refraction. There's nothing more basic than this. Well, there's reflection and refraction, but this is all kind of just joins together. So you start off with talking about what a refractive index actually is. And it's the property. Well, first of all, it's the ratio, right? Numerically speaking, it's a ratio, but in a tangible sense, it's the property of a material. So it's a property, first of all, of a material which measures how much light slows down, or how much the material itself, how much the material itself slows down light as it passes through it. So I have a material over here, and you have light passing through. If it's moving at the speed of light, which I don't know what that is, but if it is moving at the speed of light, then in the middle, how much it slows down. It's how much it slows it down. It's not this speed over here. It's the speed over here, like the change from this to this. That kind of measurement, how much it slows it down, that's going to be your refractive index. Okay. So it is calculated by dividing the speed of light, which is, in the vacuum, which is your original speed. So that's going to be your C. It's not an S, it's C. And the speed of light in the substance, which is V. So over here, that's going to be your V. Okay, so this is going to be your C and your V, and the ratio of that is going to be your property, M, which is your refractive index. Okay. Now, we tell you that speed of light is measured in C, and V is measured your thing. But as you know, N is also calculated, if I'm not wrong, in sine C over sine V, if I'm not wrong, or was it sine I over sine R? Yeah, that's the formula. So your incident angle is going to be also the same thing as your speed of light, and your your refractive angle, or your angle of refraction, is going to be the same thing as your speed of the light in the substance. Apparently these are somehow correlated, so that's something I think that you can look into further. So this is, I can give it a star and say this is like Fizzy approved of being an extra topic or extra cool topic rather to look into. Okay, I'm gonna spend that much time typing that down. Okay, so this is basic stuff. Higher refractive index can be more optically dense, which means it slows it down more. So slows more. It slows it down more. So the speed decreases more as it enters. And the speed of light over here is always going to be the same. It's always going to be C, because it's going to be air, and any photons or any particles traveling on this wave will always be moving at the speed of light. But over here, this changes depending on which material it is. This V. Okay. So now refraction. Okay. Now we're talking about refraction and reflection. So refraction occurs, specifically refraction occurs when it enters a different medium. And there's two things that happen. Well, one, it slows down, but first of all, it changes direction, either away or towards the normal, depending on the material's refractive index, and the speed changes. Okay. Over here, speed changes. That's going to be your 2. I know it's hard to see the cursor, but it's okay. Now, when the direction changes, there's 2 things to think about. There is, when it changes direction, which direction it changes to depends on the refractive index. Now, okay, this makes sense, because refractive index is the property which tells you how much it slows down, right? It slows down. And if this amount slowed down depends on the angle or direction, there's 2 directions here. Is it going towards the normal or away from the normal, right? So so you can say that depending on the refractive index, which is how much it slows it down, the angle or the direction in which the refracted ray will fall changes. Okay. Now, all these are correlated, but we can put them down into one basic formula, and that is going to be Snell's law, right? And it's used for calculations involving refraction of light, which means we need a different medium. This is important. We need a different medium, and we need two angles. One is sine I and sine theta and sine theta 2. Sine theta is going to be your incidence of material 1, and incidence of material 2 is the sine theta 2. Okay, so and this is going to be incidence and refraction. Sorry, I said that wrong, but this is going to be your incidence angle. This is going to be your refraction angle. So this is incidence, as you know, sine I, and this is going to be a refraction, so sine R. Okay, so I thought we could erase it. No, what's that about? Oh, there you go. Okay, so you have your sine I, sine R, so that's going to be refractive, and the n is going to be depending on the material. So your refractive index of the first material, and the refractive index of the second material. Now note that the refractive index of the first material times the angle to the normal. If you multiply those two things, if you multiply the angle and the refractive index of material 1. Now if we're talking about air as material 1, right, then if you're talking about air and we have a medium, well, we already first of all know that air will have a specific angle, okay, and that specific angle, if I'm not wrong, it's going to be your c, or your speed of light, and then your refractive index of air, I think it's going to be like 0 or something. I don't remember, but it's a specified value, so you don't need to really worry about this. That's why I'm pretty sure it's like sine, like 1 over sine R is like your refractive index, and that's only for air when your first medium is air, because 1 is already going to be a specified value, because air is already a specified value with like specific things in it, so you don't need to really worry about that. So that's going to be your angle. So see, when GCSE, you only learned the formula of refraction as something like this. I don't really remember the specific one. It's probably somewhere here. Is it? Okay, it doesn't seem to be, but oh yeah, sine c is equal to 1 over n, or n equals to 1 over sine c. So I was I right? Okay, I was almost right. It's 1 over sine c. So that's gonna be your formula. Oh, but then it's not sine r. Oh well, whatever. So sine c is something that you can calculate, right? And that's gonna be your n. So this is simplified because your incident material, your N1 in this case, is always going to be air, right? But your N2 is going to be something else. Your N2 it can be varied, so that's why you use this formula, because your N1 is always going to be the same. Now, when we have two different materials, let's say we have glass and we have water, or we have like, I don't know, plastic, and then we have some kind of other transparent material. Loads of different types of, alloys of plastic, right? Polymers of plastic that are see-through. That are translucent or whatever. So, or loads of like different densities of glass. Okay, so each of those N1s and N2s can be different things. Okay. Now, that's when you use this formula. You use Snell's law. Okay, that's when you use this to calculate the refraction of light. Okay. You can also calculate, well, you see, when you say refraction of light, you mean 4 things. You can calculate the refractive indexes of the two materials. You can even calculate the angles of those two materials as well. The angle in which light enters and leaves or whatever. Those angles you can calculate. And I'm pretty sure those angles are the speeds. Tell you what, let me just ask ChatGPT. Is the incident angle of a ray entering a medium the same as the speed of that ray? And he says no. Okay. Incident angle, okay. The speed typically decreases while the angle changes according to Snell's law. Yeah, that's what we discussed. And then if I mentioned if um, refractive index is sine n equals to sine c over sine r, or rather c over r, or that's what it was, right? C over r, yeah, and also n equals to sine c divided by sine r. I hope that's the formula. Then isn't c speed of light same as sine I? Sorry, incident angle. Speed of light sine c. Speed of light c and the sine incident angle sine I are not the same thing. The first equation. Oh well, okay. This is kind of cool. So I'm gonna actually just change the scene so that you can see this, because this is actually kind of dope. Window capture. Can we go for this? Alright, I think you can see that. So I can just yeah, okay. Cool. And if I want, let's just, I don't know. How do I like? We'll just like, oh shit. Oh wow. Okay. Okay, I guess not. It's alright. Okay. So over here it says you have your two different angle formulas, and although the first equations involve refractive index, they describe a different thing. The first equation relates to the speed of light in a vacuum C and the speed of light in a medium V. The second refers only to the angles of incident and angles of refraction for light passing through different media. They're not interchangeable. C represents C, C represents speed, and I represents sine of angle, while both describe refraction, sine I and sine C. Okay, fine. So although they equal, they perhaps equal, but they're not the same thing. Okay, that's that. Well, thanks you, ChatGPT. That's pointless. Just better way of saying they're not the same thing. Shut up. Okay, my fault. So now, yeah, this is important. So as we were talking about, there's two things that change, right? And that's gonna be better if I use my marker here. So there's two things that's changed. That's gonna be your direction that's changing. That's number one, and that's your speed that's changing. That's number two. Okay, and yeah, the speed changes again. It's right here. The speed which causes the direction to change. This is, I think, one of the most important points to take away from this whole, Snell's law biz is going to be this one fact, as it goes through the boundary, as it passes through as your speed will change, your direction will change. Okay, now in this example, we're referring to how n2 is more optically dense than n1. Okay, so we can see, if we can imagine, if this is air and this is glass, then obviously glass is going to be more dense. So therefore the ray of light slows down and bends towards the normal. However, so that's one thing. So we have n2, and we have n1 here and n2 here. So n2 is more dense. So but this is the upper arrow and this is the down arrow. So this is density. So this is more dense. So that means the ray of light slows down more. So if we talked about speed of the ray of light, so this one will slow down more, and this one will be, you know, less slow. This will be the same because this is n1, but it slows down now, and it bends towards the normal. So if we talked about like the angle, right? So if we talked about like the angle is an A, then the angle over here, we'll keep this as up. It'll bend towards the normal. So if it bends towards the normal, then if we have like this kind of line, right, going like this way, then the angle will be smaller. So the angle is smaller. Okay, and then in the case where n2 is less optically dense, then then it'll bend away from the normal. Okay, so this is another pretty important thing. So we'll write it again here. So you have your n, if your n2 is more dense, right, then three things will happen. First of all, your so density will obviously increase. Your speed of ray will decrease, and the angle of refraction will decrease, aka meaning that it bends towards the normal, okay. So those are just three things that you need to know, and one of those things can be used interchangeably. So it's your density, your speed of ray, your angle of refraction, leading to this whole biz, which you should just know. You should literally just think of this as one thing. Don't make sure this is one thing to you, that when the angle of refraction decreases, it bends towards the normal, and when it increases, it bends away from the normal. You want to visualize that whole thing with this diagram that I drew here, right? It's like, just remember, when it increases, when your angle of refraction increases, then you're going to go here, and when it goes here, the angle will increase as you're going over here, as the thing goes here, right? And this will only go here, this will only increase further out as the speed of the ray increases. You can think of it as it bounces, right? So it's going, and so it goes really fast, it'll bounce this way, and if it's going really slow, then it's going to bounce like, it's not going to bounce as much, so it's going to go like this. It's going to go closer, okay? So as it goes faster, the angle increases, and so the it bends away, or it goes away, or turns away, whatever you call it. So now we talk about critical angle. Now, critical angle is this is just simple definition stuff. You should know this from GCSE. You increase the angle of incidence more and more, right? You increase the angle of incidence more and more, and the refraction angle. Wait, are we talking about? Okay, no, not necessary. Okay, fine. So you increase your angle of incidence more and more, and then the angle of refraction will also increase until it gets closer to 90 degrees. So what they're saying is, okay, we have to be looking at this diagram. So if we're passing through the light from the medium and it's going over here, and it's refracting, okay? So that means now we're changing stuff up. Now this is going to be your angle of refraction, this is going to be your angle of incidence, and this is going to be your angle of refraction. Am I right here? Yes, you are right, because n1 is here and n2 is here. So when we're going from n1 to n2, okay, but you need to think of n1 being the denser medium, okay? In this case, n2 is air, right? So n2 is the denser medium. So if we can keep both of these texts in the same area, that would be useful. So over here, it says angle of incidence increases. So we're increasing your angle of incidence here. This will increase further. And as your angle of incidence, let's say it's going like this, okay? If it's going like this, then what will happen to your angle of refraction? It would probably go, I'm not exactly sure. Let's say it goes like this. So it's like this, okay? So it says here straight up, it just gives you the fact of the matter that when your angle of incidence is increased, the angle of refraction also increases. I always like putting stuff like in these arrows. So when you have I and you have R, when your angle of incidence increases, your R increases. So let's say Your angle of incidence, okay, yeah, okay, that means this is wrong. So let me just raise this. Let me say your angle of incidence is smaller over here. If your angle of incidence is smaller over here, so we'll write the down arrow, then your angle of refraction will also be smaller over here. Okay? Because this is the normal, so it's the angle from the from the normal, right? So it has to be like this. So it's like this. Right, how it's like 90, so now it's decreased to this very small angle. This one is like this. This looks like a 45. So now it's going to decrease to like maybe a 20. That's what it looks like. So it's going to decrease in both. Now the more and more you increase this angle, more and more, and the more and more you increase this angle, more and more, right? And you're going to reach a certain point where when you reach this angle called the critical angle, your refracted ray will stop going like this and it'll start increasing and it'll increase until it's 90 degrees and it's perpendicular to the normal. So when it's perpendicular to the normal, it's exactly 90 degrees. Then your light is refracted along the boundary. This is how we call it. We don't say perpendicular to the normal. We call it 90 degrees, but we mainly say that it's refracted along the boundary. Okay? And this angle, we're talking about the incident angle only. We've already said that if it's going around the boundary, then it's already 90 degrees. We've calculated this is 90 degrees. But whatever, because depending on the medium N1, this will change. And the variable angle in this case is going to be your critical angle. Okay? Your critical angle. Okay? So that's important. Now you can use, in this case, that one of the mediums is air. You can use, which has a refractive index of approximately 1. So this is 1. I was right. Then you can use the formula to find out the critical angle. This. Okay. Oh, that means whatever I was saying up there was wrong. Okay, whatever. It's okay. So you have sine c 1 over n. Okay. So n equals to sine is 1 over sine c. This is another thing you can use, right, to calculate a refractive index of which material? Of course, of only one material, because the other material is air. Now you have internal or total internal refraction, another GCSE topic. Basically, it's just talking about how after you've reached the critical angle, where's my pen? Okay, so after you reach your critical angle when you have your 90 degrees, when the angle of incidence is greater than the critical angle. So this is the critical angle that you reached over here. When your angle of incidence goes past that, let's say this was the critical angle, theta c, and it goes, this is critical angle, so it goes past that, right? When it goes past that, then it will go from 90 degrees and it'll start going this way. So now it's going this way. This was 90 plus whatever angle this is, and now you've reached your total internal refraction. This is where your incident refractive index, okay, this is in both cases where your angle of incidence is greater than the critical angle, and the n1 is greater than the refractive index of n2. This only works when n1 is greater than n2, which means the n1 is going to be denser than n2. Let's ChatGPT time. Does a higher refractive index mean the material is denser? I said dense. I said denser. Shut up. ChatGPT, shut up. Okay. Correlates, but does not always have a direct indicator. Measures how much light slows down. Density and refractive index aren't perfectly linked. It depends on both the material's optical properties. High refractive, but it's not as dense as lead, which has a slower refractive index. Has a higher refractive index than air. Okay, but water is much less dense than. Okay, but it is a basic thing. Oops. So denser materials often have higher, but it's not strict rule. Okay, so we can follow this. Okay, so n1 will so there's two factors to this. Okay, it occurs when, right? So there's two factors. One, if you can just erase this because this is a bit bothering me. One is because it's going to be your angle of incidence is greater than the critical angle, right? This will only happen when this is being followed, and your 2 is when your n1 is greater than your n2. So your n1, which is going to be your n1, n of n1 is going to be greater than n of n2. Okay, whatever this is. In this case, it's air. But if this is going to be, let's say, a glass, or this is going to be a plastic, or whatever, and this N2 is going to be less dense than this, it has to be, or else this wouldn't work, because it wouldn't work because we are going from a denser to less dense, right? So that means if this is a cleaner, or this is a less dense material, then it's going to be refracting away the more you increase the angle of refraction. In another case where this was dense, if we looked at this case over here, and this is less dense and this is more dense, and if we increase the angle here, what would probably happen? Because that's actually a good question. Because it's known. Okay, fine. If we can, okay, then we can use this Snell's law formula now to calculate that. So if we have n sine theta 1 equals to n2 sine theta 2, that means sine theta 1 equals to n2 sine theta 2 over n1, which means that there's that is not the it's not the right thing to do here. I want to find out the angle for refraction, and if I wanted to find the angle of refraction, then I would have to do n1 over n2 equals to sine theta 2. Okay, which means, I mean, it's the same thing, but this means that if as sine theta 1 increases, then this will increase, but as n decreases, or rather increases, this will decrease. So these two have inverse, these two have a positive correlation with this, and these two have an inverse correlation or negative correlation with this. So it works the same way. When you increase the angle, it will increase the incidence angle. Anyways, so I'm getting kind of off topic here, but whatever. What were we doing? So yeah, 2 factors. Needs to be a greater, that's one thing, because that just makes more sense, and the refractive index over here needs to be greater than this. Why does it need to do that is actually a good question. I was thinking that since this is a denser material over here and this is a lighter material over here, the speed will increase. As speed increases, it will the angle will increase further and further and further until it's 90 degrees. I guess that's a good enough understanding to have. What the hell? Okay, I think that's a good enough understanding to have, so we can move on. How far are we? We are 30 minutes in, and we are how many pages in? Quite a lot. We only did 1 page. No. Okay, we need to speed up a little bit. Most of these things are pretty easy. Then we talk about polarization. These are the new things. Electron diffraction. Okay, that's pretty interesting. Okay, fine. So measuring a refractive index. Okay, so this is gonna be your core practical stuff. Don't abbreviate that. Funny. Procedure of finding it. So this is gonna be your little procedure. You're gonna have 9 steps, and then you're gonna have some theory involved. Okay, so that's gonna be how it's gonna be. This is how it's divided, right? So you have your 9 steps of practical stuff, and then you have your theory of whatever. This is gonna be your theory, and it involves your results, right? So this is gonna be your results. Using results. Now, I would tend to avoid core practicals because I hate them, but let's just go through it a little bit because it'll help you with the understanding. So first of all, understand that we're trying to find only one thing here, and that's going to be your refractive index. That's what we're trying to find, okay? And we're going to have, if we're trying to find the refractive index of one solid material, that means the other refractive index is already given to us, aka air. Air is going to be our N1 here. Unless we're doing N2, but we're not doing critical angles, so it's going to be N1 is air. Place material, perspex block, whatever it's called, in the center of the piece of paper. Draw around it using a pencil. Okay. Draw the diagram of what your experiment is going to look like. The boundary of the block. Now place, and now then you want to draw. Hold on. Place the material block aside and mark a point on the outline of the material. So on the outline that you drew, preferably in the center or whatever, draw a line perpendicular. This is going to be your normal. So you're going to draw a line perpendicular 90 degrees, and this is going to be your normal. Make sure you use your little protractor to angle it. I don't know why they did it upside down here. This looks really weird, but if we were doing it the other way around, this is, let's say there's no block here, right? So you removed your block and you just have your outline. So you want to draw a little point on it, and you want to use 90 degrees on your protractor to calculate, to draw the normal. Obviously mention that you use a protractor to make sure the line is exact. And yeah, so your first step is talking about drawing the basic outline. Second step is talking about drawing the normal using a protractor. Then third step is talking about after while using a protractor, draw lines leaving the point that you have marked at 10-degree intervals from 10 to 70, where angle is measured from the normal line to the line that you are drawing. So okay, they started to tell you that you're going to be drawing your incident rays now. Okay, the way you do it is after you find your 90 degrees, we'll use this one because this is nicer. Actually, no, we're going to use my one because my one is better. So you want to start measuring at 10-degree intervals from 10 to 70 from the point. Now, look, this is hard to describe in English, I understand, but you just kind of have to do it. Now, a teacher once told me how to measure these angles. So you want to first draw your little two lines, divide it into two, then okay, I already messed it up. This is embarrassing. How do you do this? So this is gonna be your first one, and that's gonna be your second one. Then you draw this one in the middle. Then you want to draw one in the middle, another one in the middle, another one in the middle, another one in the middle. So 1, 2, 3, 4, 5, 6, 7, 8. Where's gonna be the ninth? Oh shit. Oh. Okay, so let's do. I know we're wasting a lot of time. This is actually really cool, and I want to be able to do this properly. I perhaps forgot. So there's 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 90. That's not. That's gonna be we need one more. Where's that one more? Oh, it's 3. Wait, 1, 2, 3. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Where are they? 45 degrees. The two other lines. 1, 2, 3, 4. Then 1, 2, 3, 4, 5, 6, 7, 8. Then no, he said to always do the okay, I don't know, man. This is embarrassing. Whatever. That's annoying. But, okay, so using a protractor, you want to find out the little points from 10 degrees intervals. You're going like this, and you want to draw the lines, right? You want to draw each and every single line. These are going to be your incident rays from, 10 to 70. 10 to 70 meaning that this is going to be your 10 degrees, like this, maybe this, like very thin line, like going from here to here. This degree is going to be your 10. This, well, we're not going to 90, we're not going to 80, so this is probably going to be your 70 degrees. Okay, so you want to go from here to here. You want to figure out all the incident rays for those. So we've drawn the incident rays. Now place the material back. Okay, so third step is drawing the incident rays. So third step, all about drawing your incident rays. Fourth step, just intermediate step, we're just placing the block back on. Fifth step, shine a ray of light. So immediately we're going to shine the ray of light across the first incident ray and mark the point in which it leaves the ray block, the material block. Join the point you have marked down to the join the point you have marked down to the point on the normal light at which light enters the block. Okay, so basically what they're saying is after you put down the light, right, you're gonna have this point over here, that where it comes out. This point over here where it comes out. So after then you want to take off the block, join these 2 points together. Okay, you want to join these 2 points together in a line, and then after you've done that, use the protractor and angle and measure the angle. So you want to join these 2 points down, and then you want to mark the point down on the normal line. Okay, so it just this sentence, this point just describes further where this where we're connecting these 2 lines. So now using the protractor, calculate the measure angle between this line that you just drew and the normal. This is going to be angle of refraction. So step 5 was mostly the intermediate, well, the first step to drawing the, so if angle of refraction, if calculating or measuring or whatever, if measuring the angle of refraction, which is sine r, is involved into 2 steps. The first step is going to be placing the ray down and letting the ray go through the light and marking the ray down, like marking the point where it leaves the material block. Marking that point, that's going to be your first step. Then the second step is going to be joining these 2 points together, and then join these 2 points together, and then measuring the angle between this line and the normal to find your angle of refraction. So now that we've found it, now that we've done the experiment once, we're going to repeat the 2 steps or the experiment, whatever, because we've practically done the entire experiment for one angle. So now we want to repeat these 2 steps, aka the entire experiment for all the angles, and then repeat the above method 2 more times and find the average. Okay, so this is an extra step. No one's gonna go this far, but you want to repeat the above method, as in repeat this method of doing these, pretty much do the entire experiment 2 more times, and find the average value of each refraction for each incident angle. So, basically, by the end of step 7, you're gonna have from 10 to 70. So you're gonna have 7 angles of refraction, right? Because there were 7 incident angles. So now it's saying you're gonna have 7, and for each 7, you want to do them 2 more times. You want to have 3 for each 70, so you have 21. But the point is, you have 3 for each of the 7 refraction angles, and you want to find the average of those 3. So you can use those. That's going to give you like the best accuracy. And then you want to plot a graph as usual. And this time you want to do it sin I over sin r. Those are the 2 variables that you measured. And well, sin I is going to be against sin r. Get the best fit and find the gradient. That's going to be your refractive index of the material. So hopefully your best fit will be the gradient, and it will be the refractive index of the material used. That's important. Just so that the gradient is the refractive index of the material. Wait, have you guys been able to hear the trumpet? That would be so fire. Oh my god, let's go. That'd be so funny. Wait, hold on. I think I gotta record. What the? What the hell? This is crazy. Where am I? What the hell is going on here? I don't even remember. Where is my recording? 216, 216, 216. Why are there so many 2? Oops. Hey, Shep. Sorry, guys. Second. Okay, you can hear it, but it's very quiet, which is actually like kind of good, I guess. Huh. So it also changes depending on how I change my volume. Interesting. So, we found out. So, if we go up, so step 7 just says repeat the experiment for everything. So complete the experiment once, and then step 8 says do the experiment 2 more times, then calculate a mean. That's what step 8 is telling you. Okay. Now, step 9 is telling you to plot the graph. That's one thing. So plot graph. And it's stating that from the graph, 2 things. One is what kind of graph are we talking about? And we're talking about sin I against sin r graph. It's number 1. And number 2 is we're talking about what, and we're talking about what we're going to do to the graph. Just line of best fit, always. And it's stating from the line of best fit that find the gradient. Sorry, it's not saying that. Whoops, my bad. 3 things, I suppose, then. Also find the gradient. And the gradient stating that it's going to be your refractive index. 3 things that it's telling you to do when you plot the graph. So when you're plotting a graph, when it comes to this experiment, know 3 things. 1, it's sin I over sin r. 2, you're finding the line of best fit. 3, gradient is you're trying to find, and the gradient is going to be your line of best. Your gradient is going to be your refractive index. Now you can derive. This is the theory. So you're going to derive the above. You can derive the graph by using Snell's law. your initial material is air, which has an index of 1. See, this is what we were talking about all the way 30-40 minutes ago. If n1 is going to be 1, then Snell's law equation can be simplified to this, because n1 is equal to 1. Now if you replace theta with I and theta 2 with r, because that's going to be your angle of incidence, angle of refraction, and then n2 with n to represent the refractive index of the material that you're trying to find, right? Then you get sine I equals to n equals to sine r. As we know, sine 1 is going to be your initial material, sine 2 is going to be your refractive material, your medium, and 2 is going to be the material that you're trying to find. Then you have your y equals to mx. Oh wow, that's cool. So y is going to be your this, x is going to be your this, so sine r is going to be your x, sine I is going to be your y, and the m is going to be your gradient. This is simply the equation for the line of straight line in a graph, sine I against sine r, meaning that the gradient must be n. And that's going to be your entirety of your basic reflection. Well, we didn't really talk about reflection, but your refraction, everything that you need to know for refraction. That's pretty much all done here. Nothing else, I hope. If there is something else, then you can probably see it in the next video. But the rest is pretty interesting stuff. Here we have wave behavior at an interface, where we talk about just a little bit. But this is a wave behavior. This is not, well, light is a wave. But this is not really the topic at hand. So yeah, that's pretty much everything. So yeah.